Okay, we've had a look at the resistor in an AC circuit. We've looked at the capacitor, we've looked at the inductor. Now we need to put them together, and putting them together is quite easy once we've got to this point, because basically what we've got is what we've already had a look at. So let me draw the circuit. This is just my notes there. It does get a bit tricky on the actual graph, but if we draw the circuit, we've got a voltage up there. Actually, this is not the circuit, this is the phasor diagram. We've got a voltage down there, and we've got a voltage there. What are those voltages? Well, we now know that that's VL, VC, and VR, right? And if we had to put the current phasor in there, it'd come in here. What's this saying? It's saying that the voltage in the inductor leads the voltage in the resistor, which leads the voltage in the capacitor. The circuit, if we're to draw it, becomes a, doesn't matter which order you do them in, resistor, capacitor, inductor circuit. So at any particular time, the voltage in the capacitor is opposite in phase to the voltage in the inductor. Okay? And when the voltage in the resistor is maximum, the voltage in these two guys is zero. It's really quite interesting. And we're going to see the way they add up to get your various supply voltages, because you're probably wondering, where's the supply voltage in all this? This is voltage on inductor, resistor, capacitor, and I'll show you that in a sec. These guys don't have to be the same size, VL and VC. That's obviously going to depend on the circuit and the amount of resistance and the amount of inductance. So this is L, C, and R, and that's why we call it an LCR circuit. This could be a really small voltage on the capacitor, in which case this circuit would mainly be, it would be inductance dominated, or vice versa, capacitance dominated. We'll look at how to actually calculate the voltages on the inductor, the capacitor, and the resistor, but one thing I want to look at first is how we actually find Vs. Where's Vs in all this? The supply voltage. And what we've got there with Vs is what we need to do is we need to subtract VL from VC or VC from VL. And so let's take this example where VL's like that, got a little VC like that, and that's our VR. If we subtract the VC from the VL, right? This is VC, always VC is on the bottom. Then we end up with a much smaller V there. And we then add on the VR, and that leaves us with a net vector, which is Vs. And that's the way you always do it to find your Vs. Is you subtract whichever one is bigger here, you then add vectorially VR, and you'll end up, the net result will be your Vs. Okay, we can write this down algebraically like this. Is equal to right. It's just using Pythagoras. VL minus VC is that little vector there. VR is that little vector there. We're squaring them both, adding them, and taking the square root, and that gives us Vs. So that's the formula for voltage of supply. And notice its phase is going to be dependent on which one of these dominates. If we use the angle between, say, Vs, so if this was Vs, so it'd be up there, if that's Vs, then that theta, or phi, becomes your phase angle. And if the circuit is dominated by the inductor, you get this positive phase angle. And if the circuit is dominated by the capacitor, you get this negative phase angle down here. So that phase angle, and if these VL and VC are equal, then these guys cancel out. And the only resistance you've got is the resistance from the resistor. And then you've got Then what you've got is the Vs is in phase with the VR, and that would be called resonance. So hopefully you're getting to see that. If you want to draw the graph of this guy here, again, you just rotate your little phasor diagram and plot your values, just like we did. Gets a bit tricky. It's one of the things we'll do in class.